Hello everyone, in this video I will talk about things that don't make diesel engines more efficient despite that people tell you they do. So let's get right to it. First, we've got to discuss two basic things: what a diesel engine does and how the efficiency of that can be expressed. Now, a diesel engine is a machine that uses combustion to convert chemical energy from its fuel into mechanical work. The efficiency of that process is thus mechanical work over chemical energy and has no dimension. Efficiency must not be confused with specific fuel consumption, which describes how much fuel an engine consumes per work it performs. The diesel engine is among the most efficient machines that can convert chemical energy into work. I'm not going to explain in detail how it works. In this video, I'm focusing on things that don't make a diesel engine more efficient. But to give at least a basic explanation, the diesel engine is efficient because it has lean burn and high compression. But let's get to 5 things that have nothing to do with diesel engine efficiency. Number 1, the fuel. Certain people believe that the diesel engine is fuel efficient because of its fuel containing more energy. It is rather easy to see that it makes no sense, but this belief seems to be very popular. However, if we put the lower heating value of the fuel into the equation, we can see that it has the wrong dimension. This means that the energy content of the fuel has nothing to do with engine efficiency. An engine that runs on fuel containing more energy will simply perform more work and its efficiency remains the same. The reason why people think that greater energy content increases efficiency is because they confuse fuel consumption with efficiency. An engine that can perform 100 megajoules of mechanical work and that has an efficiency of 50% needs 5 kilograms of fuel if the fuel has a lower heating value of 40 megajoules per kilogram. Pretend the fuel now contains 50 megajoules of energy per kilogram. Then the fuel consumption is reduced from 5 kilograms to 4 kilograms. However, the efficiency of 50% remains unchanged. Another reason for the energy content belief is that Euronorm 590 diesel fuel has a higher density than petrol, which means that it contains more energy per volume, which explains why the volumetric fuel consumption, which means measured in litres or gallons, is about 50% lower than what should be expected from the actual efficiency rating of the engine. But again, one must not confuse volumetric fuel consumption with engine efficiency. Yet another thing to mention here is that the most efficient diesel engines, large 2-stroke marine engines, don't even run on Euronorm 590 diesel fuel because that would be way too expensive. Instead, they run on heavy fuel oil, which contains about 5 to 10% less energy per unit of mass than Euronorm 590 diesel fuel. Side note, modern engines also often come with a methane option because it can be more economical than HFO. Number 2, natural aspiration. A common belief is that natural aspiration helps engine efficiency. However, this is not true, especially not for a diesel engine. I assume that it's widely known that a turbocharger's high-pressure turbine increases the amount of air inside the cylinder, which allows the engine to burn more fuel and produce more power. Of course, this increases the mass of burnt fuel, but since the engine also performs much more work, the engine efficiency remains unchanged from this. However, we must not stop there. One of the 2 keys of the turbo diesel's efficiency is the turbocharger's exhaust turbine. As I have said, an internal combustion engine converts chemical energy into mechanical work. In order to do so, the fuel is burnt, which releases the chemical energy in form of heat energy. The heat energy is then converted into mechanical work. However, using the last portions of the heat energy would not yield significant amounts of mechanical work, because the friction would convert the extra yield of work back into heat, and the dimensions of the cylinder would have to be large in order to even get the extra yield. This is why the remaining gases are released through the exhaust valves. However, they still contain heat, which is called the enthalpy. Enthalpy of a thermodynamic system is defined as the sum of its internal energy and the work required to achieve its pressure and volume. The enthalpy can be used by the turbocharger's exhaust turbine to increase the thermodynamic efficiency. So, in other words, the turbocharger allows the engine to waste less of the energy through the exhaust, which increases overall efficiency. The second key to turbodiesel efficiency is the intercooler that is often fitted with a turbocharger. Ideally, the air inside the turbine is cooled down during compression for maximum thermodynamic efficiency, which would be, in this TS diagram, compressing isothermally from 0 to 1. However, this is not possible. The second best thing to that is compressing isentropically from 0 to 1 prime and cooling down the air isobarically from 1 prime to 1 after compressing it, which is what the intercooler does. Number 3. Engine speed. You will often hear that the diesel engine is more efficient because of its lower engine speed, and this is not correct. If it was true, Otto engines, which are regular petrol engines, would also have lower engine speeds. And not only Ottos would have lower engine speeds, but all internal combustion engines would not be high speed at all. However, not all internal combustion engines are designed as low-speed engines, and this is because the engine speed doesn't affect engine efficiency that much. Only at very high engine speeds, the gas flow and valve operation can become a limiting factor, but box standard engines are typically not designed for engine speeds that high. When talking about low diesel engine speeds, most people are referring to speeds below the 3000 per minute mark. Even if we're comparing a very inefficient anti-chamber injected high-speed passenger car diesel engine with an engine speed of 3000 per minute against a huge displacement low-speed Acroyd engine with an engine speed of 600 per minute, the awfully inefficient diesel engine is still about 15% more efficient than the Acroyd engine, which does not only illustrate that the engine speed doesn't matter, but also that the Acroyd engine is not a diesel engine despite running on the same type of fuel. As we have seen, engine speeds don't matter that much, but piston speeds can do. That is because at higher piston speeds there is more friction and thus more mechanical losses occur. This is true for any kind of internal combustion engine, and thus production engines for passenger cars that are designed to be economical and reliable typically have piston speeds in the 13 to 15 meters per second range, no matter which operating principle they use. So despite having slightly greater strokes and thus lower engine speeds, the piston speeds in car diesel engines aren't necessarily significantly slower compared to their Otto counterparts, what you can see here in this example. While the system of the diesel engine itself may not be significantly more efficient due to lower engine speeds, the system of the entire vehicle can be. In a road vehicle, the rotational speed of the wheels often does not match the rotational speed of the engine's crankshaft, which is why road vehicles need a gearbox. For instance, a car with 477mm wheels that drives at a speed of 108 km per hour will have a wheel rotational frequency of approximately 1200 per minute. If the engine speed is 3000 per minute, it needs to be reduced by the gearbox and the differential. However, both the gearbox and the differential reduce the system of the vehicle's overall efficiency by a certain degree, simply because they convert mechanical energy back into heat energy through friction. This is why super efficient vehicles, rather vessels, don't have a gearbox. I'm talking about large container vessels with two-stroke diesel engines. Watercraft typically have a propeller for propulsion, and a large low-speed propeller is very efficient. The diesel engine in large watercraft is designed to deliver the right amount of torque at the best propeller speed. If this speed is 102 per minute and the torque requirement is 7,500 kN, then the engine speed is also going to be 102 per minute and the torque output is going to be 7,500 kN. This eliminates the need for speed and torque conversion in a gearbox. However, it also drastically increases the engine dimensions, but in a large marine diesel engine powering a gigantic ship, this is acceptable. As the final example for engine speeds, I would like to compare the world's largest diesel engine, the Wärtsilä Artiflex 96C, against the world's most efficient four-stroke diesel engine, the Wärtsilä 31 series. Both of these engines are marine diesel engines, but with slightly different purposes. The Artiflex 96C is meant for directly driving the propeller, whereas the 31 series is meant for driving an electric generator. The technical specifications of these two engines are very different from one another, yet both of these engines can convert more than 50% of their fuel's energy into mechanical work. Number 4. Torque. It is often said that diesel engines are more efficient because they produce more torque. But that makes no sense. Fast said, torque depends upon an engine's aspiration and its displacement. So turbocharged engines produce more torque, and as I've said, especially turbo diesels are more efficient. And as we have seen with watercraft, high torque allows the engineer to design an engine with a low crankshaft speed, eliminating the need for a gearbox, which improves overall system efficiency. But this has nothing to do with the engine efficiency. I believe the reason why certain people claim that more torque makes an engine more efficient is that it makes accelerating a car easier because it requires less engine speed. But accelerating a car in general requires more power than just driving without acceleration, and using more power moves the load point of an engine further towards the ideal spot. So in theory, accelerating makes an engine run more efficiently. The reason why engines for passenger cars are more efficient when driving in a city is not that they produce more torque, but that they run more efficiently in low load situations. Now, when comparing classical diesel engines against classical petrol engines that rely on a throttle valve to manipulate their torque output, which means no fancy valve manipulation systems like VTEC or Vanos, then diesel engines are especially more efficient in such situations because they don't have a throttle valve. A good example for a low situation is moving a car in a city from one stoplight to another. However, at the stoplight, when the car is not moving at all, both diesel and petrol engines are indefinitely inefficient because they use fuel energy but perform no work. At this point, I would like to make yet another example that illustrates the point. The Mercedes-Benz OM636 diesel engine and the Mercedes-Benz M136 petrol engine both have the same displacement and were both intended for more or less the same purpose, powering a passenger car. The major difference between these two engines, if we ignore the operating principle difference, is that the OM636 has a cross-flow cylinder head, whereas the M136 is a flathead engine. So the OM636 is superior in terms of its gas flow, which should improve performance. Yet, the M136 produces about 10% more torque than the OM636. However, the OM636 is far more efficient despite producing less torque, so engines with more torque can be less efficient. Number 5. Engine displacement. A popular car magazine claims that one would need an 8-litre petrol engine in order to access the same amount of power as with a 6-litre diesel engine, and because the diesel engine has less displacement, they conclude that it is more economical than a petrol engine even if petrol is less expensive than diesel fuel. This conclusion only works if they assume that the diesel engine is more efficient because it has less displacement. And well, displacement doesn't affect efficiency that much. As we know, internal combustion engines convert chemical energy into work by means of combustion. This means that the engine should not let any heat energy escape, and that means that the engine should have a small surface area. Now, the more volume something has, the less surface area it has compared against its volume. The conclusion now is that a large displacement engine is more efficient than a small displacement engine because it offers less opportunity for the heat to escape. It can't be the other way around. In real engines, though, this effect only comes into place with really large industrial engines. Thus, an 8-litre diesel engine is not going to be significantly more or less efficient than a 6-litre diesel engine of the same type. And the cause of the 6-litre diesel engine's higher efficiency when compared against an Otto engine is not its displacement. But that's it for this video. I hope that you learned something. Leave your comments and questions down below, and I will see you in the next one.